Unit 6 is all about magnetism and learning about magnets and their practical uses. In Notes 1, we were going to discuss how magnets work. If you're like me at some point in your life, you probably wondered, how do magnets work? We understand what magnets are. They're objects that can stick to either other magnets or they can stick to metals. And we know that not all metals are going to be magnetic. We know that if we stick a magnet to something made out of iron or steel, it will stick. But if we stick a magnet to like aluminum foil, it will not stick. So we're going to learn all about magnetism and how it's created and what magnets are used for. So you might have wondered, what are magnets made out of? Well, we know that only certain elements are magnetic. Specifically, only some metals, not all metals, but only some metals are magnetic. And some examples of that are going to be iron, cobalt, and nickel. Those are going to be the most common forms of magnets, especially iron, because a lot of the Earth's core is made up of iron and also nickel as well. Um, so these metals can act like magnets when their magnetic domains are aligned. Okay, so what exactly is a magnetic domain? Well, we know that any single substance of metal is made up of atoms. So we learned about that last semester in the chemistry portion. We know that it's made up of atoms, and atoms are made up of protons, neutrons, and electrons. The protons and neutrons, they're just kind of sitting there in the middle of the nucleus, but the electrons, they're spinning around the nucleus. Okay, so when you have a region of atoms where the are spinning in a certain direction, that is called a magnetic domain. So let's say we focus on just this portion right here where this arrow pointing up. That means the electrons in this portion, um, they're they are spinning in such a way that it's creating a magnetic field pointing up. All right, and so that's in one direction. For this specific portion of, let's say, iron or nickel, again, they're spinning in one direction and creating a magnetic field going in an opposite direction. So they're just kind of random in an unmagnetized object. So you can see here in the bottom one, if they're all going to be aligned here, they are going to create a greater magnetic field. So if all of the domains, if all of the electrons are spinning in the same direction and kind of facing the same direction, then the substance will become magnetized and generate a magnetic field. All right. To kind of create an analogy for that, I like to compare this to, let's say you have a crowd of people. So we're taking a look at this upper image here, where all of the people are kind of looking in different directions. You might have a couple of people, for the most part, looking in one direction, but there's a lot of people, just facing all sorts of different directions. You can kind of compare each person to an atom in a certain metal or a certain substance, and they're all facing different directions. So that's going to be like an unmagnetized object. Let's say you have a bunch of people focusing their gaze onto someone, like for instance at a concert or maybe like at a church or something like that. You have a bunch of people facing the same direction. So that's what's going to look like for the atoms in a magnetized substance. All right, so taking a look at magnet, we have these things called permanent magnets, and these are created when a magnetic metal is surrounded by a strong magnetic field. Okay, so when we have a very strong magnetic field and we have a substance of a metal that is cooled from its melting temperature, it will create a magnetic field itself and create a permanent magnet. So over here we can see that we have this sample of metal. Let's say this is iron, and it's a permanent magnet, and it has a north pole and a south pole. All right, and one thing to note here is that if we break this magnet in half, if we were to shear it in half like this, we are not going to divide it in simple north pole and south pole by itself. We're going to divide it into north and south um, for both of those. So when a magnet is broken, it creates two smaller magnets with the same poles. All right, to kind of go back to that crowd example, if we have if we compare like this entire group of people as one magnet, because they're all individual atoms. Let's say we just got rid of this row of people and like we moved them somewhere else and we got rid of all the chairs. We've effectively divided the crowd in half, but they're all still facing the same direction, right? So you can still see the front of the people and the back of the people. So you have it north and south pole. All right, so if we break, one more time, if we break that magnet in half, we don't create only a north pole and only a south pole. Each individual magnet half will now have its own north and south pole. All right. The strength of the magnetic field will typically be weaker, however, because this is now a smaller magnet. Magnets do gain strength if you do stack them to a certain point. But in this case, when we break the magnet in half, we are creating two smaller magnetic fields. All right, so last unit in electricity, we learned how a positive and a negative charge will attract because opposites attract. That is also the case with magnetic poles, except we don't have positive or negative in this case. We have negative. We have a north pole and we have a south pole. So opposite poles will attract just like how opposite charges attract. So north pole will attract a south pole, and you can see the magnetic field lines going from north to south like this, and they kind of go in little arcs or circles. So they form these loops. This is an image of two bar magnets, and then there's some iron filings here, and the iron filings will just follow the magnetic field lines. All right, just keep in mind that these magnetic field lines are not going to be in 2 dimensions. They are 3-dimensional, even though they're represented on this picture as a 2-dimensional. All right, so just like with charges, like charges repelled, so the same poles will also repel. If we have a north and a north, we can feel them repel. And same thing with the south and the south, they will also repel. So you might have played around with a couple of magnets at some point in your life where you try to push 2 magnets together, but they're repelling each other. We notice that the closer you bring the magnets to each other, the stronger the field is between them, the stronger the interaction is between them to repel. Okay, and that is called the magnetic force. The magnetic force is the ability for the magnets to affect other magnetic materials around them. It can be either repulsive or it can be attractive. Okay, and it's typically affected by these things. If an object is closer to a magnet, you can feel more force. Okay, so let's say I'm holding a magnet like a refrigerator magnet, and I'm across the room. I'm nowhere near the refrigerator. You're not going to feel much force. Is there a force? Yes, but it's a really, really small value that you can't even feel. But the closer you get to the refrigerator, the more you can feel. And if you're maybe like an inch away from the refrigerator with a magnet, you can definitely feel the force of that magnet. The stronger the magnetic material, the more force it has. There are different types of magnets. The small ceramic ones that you can buy in pretty much any hardware store, those are going to be pretty weak, and they're often used as the back for the refrigerator magnets. But there are other magnets like neodymium magnets that are much stronger because of the material that they're made of, and so they have a greater magnetic force, and they're very difficult to rip apart if you get 2 of them stuck together. All right, so let's take a look at practice problem number 1 really quick. What happens if you cut a magnet in half? Determine if these answers are correct or incorrect and explain why. A, you get 1 magnet with only a north pole and 1 with only a south pole. B, you get 2 smaller pieces, each one with its own north and south pole. C, you get 2 unmagnetized pieces. Or D, you get 1 magnet with 2 north poles and 1 magnet with 2 south poles. So pause here for a second and try to think about it and try to come up with the correct answer. So if you thought about it, the correct answer, of course, is B, and all the other ones are incorrect. You do get 2 smaller pieces, each one with its own north and south pole. But that, again, the magnetic strength of that magnet is going to be much weaker than it was previously. All right, so for a magnetic field, like I mentioned, you see that it goes from north to south and kind of forms these loops. This is the area around a magnet where the magnetic force could affect other objects. Okay, so when you can start to interact with other objects using a magnet, you are interacting with that magnet's magnetic field. Okay, so we have a bar magnet here with the north and south pole clearly labeled. If I start to like move things and interact with them, then the magnetic field of that magnet can be felt on those objects. It could be as harmless as, again, hanging stuff onto your refrigerator or something metal. But sometimes if you have like a really strong magnet, it can be very dangerous for some things. Like if you were to have something magnetic near a credit card or like a gift card, it could completely wipe all the data off of that card. That's why it's typically not a good idea. If you have a gift card that has a swipe bar on the back, that is a magnetic strip on the back of the card. You probably should not want to keep that on your refrigerator hung up by a magnet because it can wipe all of the data from that gift card. Same thing goes like a credit card or anything like that. But most of the time, I think gift cards they have a barcode that is just printed on the back, so it should be fine. Old box TVs. Sometimes you can take a magnet and swipe across the old box TVs. Again, that's not good for the TV. It would probably break it after extended exposure to that. And then giant MRI machines. If someone is going to get an MRI, they need to remove all metal from their body because the MRI will act as one giant magnet. All right, so magnets, of course, will attract or repel another because of these fields. So north and the north will repel, south and the south will repel, but north and south, they will attract. All right, and so when they do attract, the lines always go from north to south. Okay, so the magnetic field line's always drawn from north to south on a magnet, north to south, just like this. Or if you have a U-shaped magnet, they go like this, north to south. And they always form these things called closed loops. Okay, so these loops are closed. So you can see here in this picture that the North Pole has a line that goes all the way to the South Pole. Even though these top lines on the North Pole and the bottom lines on the South Pole are disconnected, they're just kind of going outside of the picture. They would be connected. If they don't connect, then of course they're not going to form a loop, and the magnetic field can no longer be felt there. And once again, they are three-dimensional. This is not a two-dimensional magnetic field, so it is three-dimensional. And I have a video to show you to kind of exemplify that. So let's go check that out really quick. All right, so taking a look at this video, what we have in this video is a plexiglass cube. And so plexiglass, you can see through it. It's similar to glass, except it doesn't shatter the same way. On the inside of the plexiglass cube, it is sealed with mineral oil on the inside, and there's also black flakes, and these black flakes are going to be iron shavings. All right, you can also see this tube down the center, and this is a hollow tube that you can drop a magnet in from the top. All right, so what we'll see here is I'll unpause, and right now the iron is precipitating downwards because it is denser than the mineral oil. As soon as the magnet is dropped in, though, you can see that the iron is going to interact with the field lines. And if we go ahead and get a good image here and just pause, let me go back to the first one. I think that was a better example. You can actually see like these arcs forming with the iron shavings. And these are these closed loops that we're talking about going from North Pole to South Pole. So we'll just watch this one more time. So we'll go before the magnet, iron precipitating downwards, magnets in here, and now you can see these loops form. And the loops are going from North Pole to South Pole. And of course the magnetic field is going to be strongest closest to the poles of the magnet. So you can see here at the South Pole or North Pole, there's a large concentration of iron filings. Same thing with here on the opposite end at the other pole, there's a large concentration of iron filings. But in the middle, not so much. So that tells us that the magnetic field is going to be strongest at either ends at the poles. All right, so we'll just go through this video. Just see one more example of how the magnetic field lines start to form on top and on bottom. And this is just to spin it around and show you how this is three-dimensional and how you can see it from all sides. Magnetic fields can actually be detected using really small objects that we're pretty familiar with, known as compasses. What is a compass? And basically, it's going to be a small magnet that can rotate when placed in a magnetic field. So you might not know this, but the needle that's inside of a compass, that is actually a small magnet. And it basically spins to tell us which direction is north on the Earth's magnetic field. So another thing you might not have known is that the Earth has its own magnetic field. It's drawn something like this. So you might notice that we have a North Pole and a South Pole, just like we do with a normal magnet. But the magnetic North Pole is actually closest to the geographic South Pole. And the magnetic South Pole is actually close to the geographic North Pole. So it's kind of confusing, but that's just the way we orient north and south with the magnetic field. And they're not going to be exactly on top of it, but for the most part, they're going to be relatively close. So the North geographic pole is actually somewhere like right here where this red line is, but the South magnetic pole is direct center is going to be somewhere right there. So it's a little bit off. And the same thing is true on the south pole. The south geographic pole is like right here. And the north magnetic pole is going to be a little bit off. All right, so they're relatively close to each other, but they're not exactly going to be right on top of each other. The Earth's magnetic field is created by the different metals that are inside the core and how they have a magnetic domain facing a certain direction. One thing that we've noticed is that the magnetic fields for the Earth have actually been moving. The actual north and south magnetic poles have been moving throughout time. So what we notice here, if we're taking a look at geographic north, so on this map, geographic north is going to be right here. We've been tracking the location of the magnetic south pole through time. In 1831, the geographic south pole is right here. It moved a little bit in 1904. And then there was a couple of world wars that happened between this time, so maybe measuring the South Pole wasn't top priority at the time. But then afterwards in 1948, we measured it again. It was right here, 62, and so on and so forth. And through the decades, it has moved. And then the most recent measurement in 2001 shows that the magnetic South Pole was right over here, which on this map corresponds to right about there. Still not exactly on the geographic North Pole, but is getting closer and closer. If the magnetic South Pole was moving, that also means that the magnetic North Pole was moving. So this is a map of Antarctica where we have the South Pole. Right there is the geographic South Pole. And we notice that the magnetic North Pole is actually moving further away from the geographic South Pole. So the latest measurement that we have here is 2005. It's not even in Antarctica anymore. So it's getting further and further away from the geographic South Pole. All right, so let's work on some practice problems here. We've got a couple of multiple choice questions, so let's go ahead and try to answer these. Number 2 says, which type of magnet can be easily magnetized and demagnetized? A, permanent magnet, B, natural magnet, C, hard magnet, or D, soft magnet? Well, if it's going to be able to be magnetized and demagnetized relatively easily, that's going to be a soft magnet. We didn't really talk about that, but a soft magnet is a term for something that can be magnetized and demagnetized relatively easily. Practice problem number 3 says blank poles of a magnet repel while blank poles attract one another. So is it like and opposite, opposite and like, north and south, or south and north? Well, we know that like poles of a magnet will repel while opposite poles will attract one another. Practice problem number 4 says a region where a magnetic force can be detected is called the what? An electric circuit, gravitational attraction, magnetic field, or potential circuit. The answer, of course, here is going to be magnetic field. Practice problem number 5. The north poles of two different magnets will blank one another. Will they attract, repel, cancel, or none of the above? Well, two north poles, since they are the same, they will repel. All right, practice problem number 6 says magnetic field lines always form straight lines, intersecting lines, ellipses, or closed loops. Well, we learned studying from the iron shavings in that cube, we know that magnetic field lines always form closed loops. Practice problem number 7 says a magnet on a pivot that can rotate freely is called a what? It is called a pole, a compass, a hard magnet, or a field line. Well, the answer to that is going to be compass. So a compass is basically, once again, a magnet needle that can pivot on the center and can rotate freely. So that's a compass. Number 8 says the blank north and south poles are not aligned exactly with the magnetic north and south poles of the Earth. Is it geographic, soft, hard, or migratory? That is going to be the geographic north and south poles that are not aligned exactly with the magnetic north and south poles. All right, number 9, Earth's magnetic field lines run from A, magnetic north to magnetic south, B, geographic east to geographic west, C, geographic south to geographic north, or D, magnetic east to magnetic west. The magnetic field lines are going to be normal magnetic lines that behave just like any other magnet, which run from magnetic north to magnetic south. All right. If you answered geographic south to geographic north, remember that the magnetic north and magnetic south, even though they're close to the geographic south and geographic north, they're not exactly on top of them. Finally, practice problem number 10. A magnetic force is the force due to interacting what? Magnetic fields, poles, objects, or permanent magnets? We know the answer to this, of course, is magnetic fields. All right, so that concludes Unit 6, Notes 1 on magnets.